So, everybody, thanks for being here. My name is Roman Markovic, and today I want to present you PISE, which is a tool we developed as part of my thesis at the Technion. The tool performs protocol inference using symbolic execution and automata learning.
First, what exactly protocol inference is? Well, assume we're given a binary that implements some protocol. It can be network protocol or actually any other protocol. And we would like to know the different states the different states of the protocol. More specifically, we would like to know, we would like to extract this state machine that explains the protocol. And we would also like to know the different message types that cause the protocol to move from one state to the other. Well, this is an example for a state machine, and R : denotes that the message is to be received for this transition, and S : denotes that the message is to be sent regarding the transition. We'll also like to know that each transition is actually a group of messages. There is a common property to all the messages in the transition. For example, the receipt2 message, when received, it actually be any message that begins with receipt2 and then a colon. The motivations for protocol inference are finding bugs in protocol implementations. It can also be useful for finding backdoors installed by attacker before program delivery. And it can also be useful for researchers who want to analyze a malware found in the wild in order to learn its protocol. Manual protocol inference is possible, but it is difficult, and it can take even a sophisticated researcher days or even weeks. This is because programs who communicate in the network usually do a lot of more stuff and not only composing and receiving messages. So the goal of our research was to automate this process as much as possible. More specifically, we assume that we are given a binary code, a program that implements a protocol, and we want to extract both the state machine of that protocol, but also the messages format for the different transitions in the state machine of the protocol. So yeah, automatically from the binary code, we want to get the state machine and the formats. Regarding the assumptions of our work, we assume protocol regularity. This is because a method we use for learning state machines. Regarding what we do not assume, like previous works did assume, we do not assume that we have access to previous network traffic. We also do not assume that we have an active protocol peer that we can interact with and test if we get the protocol correctly. And we do not assume that we have source code in a human-readable programming language. And we also do not assume to know in advance the different message types of the protocol. So let's dive in to the under the hood of our method. Well, our method is actually composed of two components. The first is the learner, which uses an algorithm to learn the state machine. This algorithm is actually called the Gh0st RAT algorithm. It is a well-known algorithm for learning a state machine, more specifically an automata. And this algorithm works by asking queries, a component called teacher, and building a state machine according to the answers of the teacher. Now, the Gh0st RAT algorithm works in terms of alphabet, which is the symbols that appear on the transitions of the state machine. In our case, the alphabet is the message types, are the message types of the protocol. So how it actually looks like when we use the Gh0st RAT protocol, the Gh0st RAT algorithm for protocol inference. Well, assume we analyze the following protocol, and we analyze it from the point of view of the server. Now, the Gh0st RAT algorithm actually asks queries about sequences over the alphabet. So, for example, it could ask if the sequence of receiving init message initially and then sending a start message is valid for the protocol. And according to this protocol, in the point of view of the server, the answer would be yes. In contrary, the sequence of receiving init and then receiving init again, the sequence is not valid for that protocol. Right, so the Gh0st algorithm will continue learning the state machine by issuing more queries like this, and will finally come up with the state machine. How do we actually answer such queries issued by the learner? So remember, the learner asks if a sequence of message types is valid for the protocol of the binary. Well, our teacher is actually composed of symbolic execution. The symbolic execution actually analyzes the binary we are given, and we'll see that in a moment. But remember, we said that we do not know in advance, or we assume that we do not know in advance the message types of the protocol. So for simplicity, let's assume for now that we do know those message types, okay? And we'll later figure this out. Let's talk a bit about what symbolic execution is all about. Well, in symbolic execution, the program is being executed while assuming program inputs are symbolic values. This way, we can explore the entire state, the entire executions of the binary. So, for example, variables x and y get the symbolic values a and b accordingly here. And when the symbolic execution executes this code, and it gets to the conditional branch, for example, that x is greater than 0, well, in this context, the value of x is actually a plus 5. So in the true branch of that condition, the symbolic execution knows that the program input must hold the constraint that, the program input must hold the constraint that a plus 5 is greater than 0. Well, this way we can also add constraints of our own. So let's say that we want to find all execution paths that match that a is greater than 3. Then symbolic execution will leave us only with these two executions. And if we had a constraint that b equals to 2789, then we are left only with one execution that matches these two constraints. All right, so how do we use this for answering the queries about sequences in the protocol? Well, let's see what happens here. So whenever a message, for example, the program begins with receiving a message, what we do is we add a constraint for that message. Worth mentioning that a received message is actually an input for the program, so it is a symbolic value. And at that point, we add a constraint for the symbolic execution that this message is of type init, making the symbolic execution discard the false branch that checks if this message is init. Then when the program sends a start message, we also add a constraint that this is a start message, and the symbolic execution actually validates that this is the message being sent. And when a message is received again, and it is data message, then we also add a constraint that the message is data, making symbolic execution discard execution paths where the message is not data, leaving us with one execution path that is valid according to the constraints. Therefore, we can conclude that the binary can actually follow this sequence of message types, and we say, okay, this sequence of message types is valid for the protocol. In contrary, let's see what happens for an invalid sequence. So when we check for the sequence of receiving data initially, and we constrain the symbolic execution at the first receive for receiving data, then the true branch that checks if the message's data is discarded, leaving us with a branch that exits with error, and therefore we conclude that the sequence is not valid for the protocol. All right, so as we said, we actually do not know the message types in advance, so we need to solve this point. Well, what we do is that we update the classic L-star queries that ask if a sequence is valid, and we also say whenever a sequence of message types is valid in the protocol, we also get the possible message types, all message types that can follow this sequence in the protocol. Let's see how we do that. And we also extend the L-star algorithm a bit in order to handle accumulating the alphabet or the message types while the method runs, so that the alphabet is empty initially and it grows as the algorithm runs. Well, let's consider the query of receiving init message types initially, and let's see how we probe for the message types that can follow this sequence. So after the symbolic execution constraint the program to receive init initially, and we resume the symbolic execution, and in this case we resume all executions that match this sequence, and then there is a send of another message. Then we get concrete values from the symbolic execution for all for possible messages that can appear in the sent buffer, and we'll later see what we do with those examples. But first, let's see another example for probing the message types that can follow receiving init initially and then sending a start message. Well, in this case, we continue symbolic execution from the point where a start message is sent already. And right after that, there is a receive for another message. Now, we call that receiving a message is actually receiving a symbolic value. We have no constraints on that because the program just received it. So what we do is we present a novel approach here to learn message types being received. What we actually do is we resume the symbolic execution for another certain of instructions, another amount of instructions, and wait for the message to be passed. Now, when the message is passed, the symbolic execution actually go through conditions that generate constraints on the received message. So in this case, for example, if we receive a message and then enter into a true branch that checks if the message begins with data, symbolic execution has a constraint that message begins with data, and this way we know the constraints required to reach this path, letting us know how the binary passes and what it expects the received message to be. So in general, we have example for messages, concrete messages that are sent or received by the binary. What we do in this step is we take those example messages and we use a naive approach here, a very simple one that we found to be working, and we extract the common bytes of the example messages. For example, in this for these three examples, we find that the common features are they all begin with receive 2 and then colon, and actually we generate a message type to represent all the received 2 messages. We use predicates because this way we can insert them to the symbolic execution as constraints. So to tie it all together, So to tie it all together, we have the L-star algorithm. It asks questions, and the symbolic execution checks the questions, which are sequences of message types, against the binary, and responds with the sequence, whether the sequences are valid for the protocol or not. And if the sequence is valid, it also provides the message types that can follow the given sequence. So let's see a run of our algorithm, a simple run of our algorithm. Well, initially we do not know message types of the protocol, so the set of message types is empty. And then the learner asks if the empty sequence is valid. And symbolic execution says, yes, the sequence is valid. And the message type that can follow is receiving init. So this message type is added to the set of message types. And then the L-star can keep asking questions. And for example, receiving init, it gets 3 more message types that can follow and adds them to the set, and then asks more questions and gets more answers. In this case, we do not reveal new message types. And for example, it can ask questions and of course get an answer that the sequence is not valid for the protocol, and more questions and more sequences to ask. And we are finally get the state machine for that protocol. Regarding an equivalence query, which is the second query of the L-star algorithm, it is a query that checks if the state machine we learned is correct or not. We use an approximation that is presented in the original L-star work and run a test suite. We also use our extended membership queries to also discover missing message types that might be missing from the state machine. Here is an example for our method's outputs when analyzing a more complex protocol. It inferred the state machine and also the different message types and their prefix. So our method actually uses Angar as its symbolic execution engine. We chose Angar because it was easy to research and develop with. And the execution engine actually can be replaced. The method is actually abstract and can use different execution engines underneath.